Well, hello, good people. So very good to see you all here today in such a virtual format. Today, we are going to be talking about the history of the nature and speed of light. And when we talk about the history of the nature and speed of light, we're not talking about like the history of how light gained its properties or gained its nature. We're talking about the history of how humans discovered the nature that light had the whole time. This is the beginning of a new-ish unit. We are starting unit 9. Oh, that's terrible 9. That's just awful 9. Okay, I'm so sorry. Don't be perfectionistic, but it's so hard when your 9s look awful. 9B, which is all about light and color. Our last unit, Unit 9A, was all about light and optics, and we talked about mirrors and lenses and how those things work and how light plays with lenses and how mirrors play with lenses and all those kinds of things, but we didn't really talk about what light is or how color works. Well, that's this unit is where we talk about like what actually is light and what actually is color and how do we actually see all those things. We're going to start today by talking about the speed of light and our history of coming to understand the speed of light, and then we'll end today talking about our history of coming to understand the nature of the characteristics of light. So that is our game plan for today. Shall we move onward? I think yes, if I can figure out just that one little technical issue, which is how do I change slides? Okay, that did not work. First, let's clear out all my drawings. Then let's move this up here. Then let's click that button and check it out. We're there. We're going to be going through a course of 3 experiments, and in these 3 experiments, we're going to go through the course of history of how we actually discovered the speed of light as we now know it today. We begin with Galileo, who decided that he wanted to do an experiment in order to figure out the speed of light. Now, the experiment that he did was a very crude experiment that was very similar to your speed of sound experiment. And he had no real success due to enormous reaction time error. Here's what happened is that Galileo went on to one end of the football field. He sent his friend onto the other end of the football field, and they both had lanterns. And he said, "Hey, buddy, old pal, over there, go ahead and lift up the little door on your lantern. And when I see the light from your lantern, then I'll open the little door on my lantern." And they were going to do that in sort of a pulsy kind of way, like the same way that you did where you hit the things together on the football field to like make the sounds. That was kind of his game plan. Well, the problem was that he just quite couldn't get the reaction time fast enough. He saw no apparent difference between when his friend would lift up his lantern and when he was supposed to lift up his. It was just way too quick. And so Galileo came to the conclusion that, well, you know, this stuff, this light, is probably either so fast that humans will never be able to measure it, or it's infinitely fast. And so he said, "I give up. The task is impossible." So not a lot of things really came from this experiment except that it taught us that light is very, 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 very fast. The next experiment, if I can change the little slide that we're on, that would be just oh so phenomenal. Let's see if we can make it happen. Look, I clicked the little arrow, or I did believe myself to have done that, but it's not really okay. Yes. The next experiment that we're going to look at was an experiment by a dude by the name of Ole Romer, or Ole Romer. I'll show you how we spell it. Ole, not like my good old friend Romer, but like O-L-E. Crazy first name. Ole Romer. That's an R-O-E-M-E-R. Now, Romer wasn't really the type of person to like be studying the speed of light. That wasn't really what he set out to do, but he did love astronomy. And so what Romer was doing is Romer was tracking the orbit of Io, which is one of these moons around Jupiter. So he had Jupiter out here, doop-a-doop-a-doop-a-doop-a-doop. Here's another picture of Jupiter in Jupiter's little orbit. And what he was doing is he was tracking the movement of this little moon all around Jupiter. The moon's name is Io. We'll draw Io on here. Deep. Okay, so he's watching Io as Io circles around Jupiter just like this. And he was counting how often Io would dip back behind the other side of Jupiter. Now, when Io got over here on the other side of Jupiter, Romer could not see sitting on Earth over here. Let's draw Earth with color so then you know it's real. Here is Earth. Here is the sun. All of our favorite planets and stars. Okay, not to scale, obviously. Okay, so Romer sitting at Earth, when Io, this little moon, dipped back behind Jupiter, well then on Earth he could no longer see the little moon Io. We had a little eclipse situation. And so he was measuring how often he would see these eclipses. And so Romer was keeping track of this data for like years and years and years. I mean, this man was dedicated to tracking this little moon's action all over the place. So he was keeping these data for years and years and years. Well, he started to notice that something weird would happen over the course of the year, that there would be times when the eclipse came too early or times when the eclipse came too late. And he said, it seems that this is not because Io is just going too slow or during parts of the year or times that Io is going too fast. He said it must have to do with where the Earth is relative to Jupiter. He said because the Earth is going around the sun much faster than Jupiter is going around the sun. And so sometimes the Earth is way closer to Jupiter if the Earth is on the front side of its orbit, but then sometimes if the Earth is on the back side of its orbit over here, well then it's way far away from Jupiter. And so here's what he said, here was his conclusion, is he said it must not be that Io is just taking more time to get to the other side. He said it must be that the light is taking more time to get to me when when Jupiter is really far away from the Earth versus when Jupiter is closer. Now here was his approximation. He said when Earth is closer to Jupiter in its orbit, it takes about, let's do this in blue, such a solid color. He said when Earth is closer to Jupiter, like for this short distance, he says it looks like the eclipse gets there 11 minutes too early. In other words, the light gets to him 11 minutes faster. Then he said when we're over on this side, far away from Jupiter, it looks like the light gets there 11 minutes late. So here where it's 11 minutes early when he sees the eclipse, and here he sees the eclipse 11 minutes late. And so he came to this conclusion that it must take light, if this light is getting 11 minutes early and this light is getting there 11 minutes late, it probably takes about 22 total minutes for the light to cross the orbital path of Earth, because it would take 11 minutes less if it didn't have to take it at all, and it would take 11 minutes more if it had to do an extra half. If it was perfectly in the middle, it would land right on time. So he said it must be that it would take a total of 22 minutes for light to cross from one side of Earth's orbit to the other. Well then, he said, this is very interesting. Oh gosh, wow, I'm doing so many things right now that I don't want to do. He said, this is very interesting. Oh, how am I orange now? Oh gosh, this is just embarrassing. Okay, you get the idea. It takes 22 minutes for light to cross. He knew the distance of the Earth's orbit, and he said, wait a second, I got a distance, I got a time, I can calculate a speed. And so what Romer did, and actually he didn't do it, but another dude who we'll meet later in the story, he actually made this discovery by the name of Christian Huygens. But he said, I got a distance. The distance is Earth's orbit. He said, I got a time. This, by the way, pen is crazy. It makes all of my letters all like boxy and angly. It's kind of weird looking. So if you can't read anything, I am just so deeply apologetic. Okay, so he had a distance, Earth's orbit. He had a time that he thought it would take for light to cross Earth's orbit, which was 22 minutes. He divided those two things, and he said, well, would you look at that? I have an expression for the speed. That was supposed to be a v. He said, I have an expression for the speed of light based on how much extra time it takes for light to go an extra distance. So he came up with an actual number for the speed of light. Now, his number for the speed of light was not accurate for two reasons. First, because this estimation of these 11 minutes wasn't quite right. Second, because the known distance of Earth's orbital radius was not quite right at the time. So his number wasn't totally and precisely correct, but it was in the right kind of ballpark. He said it had to be something like 1.00. Those are zeros, by the way. I know they don't look like zeros. Let's do a little reformation work here. Okay, 1.00 times 10, that's a 0, times 10 to the 8th meters per second-ish. He said it's somewhere in that ballpark, somewhere in the range of 1.00 times 10 to the 8th meters per second. Now, this wasn't a precise number, but it was the closest thing we'd ever had to an actual number. Previous to this, we'd had no number, and now we had something that was in the right ballpark. He most certainly got the 10 to the 8th right. So it was our first time actually coming up with a good number here, and that was Ole Romer's contribution to the speed of light. Now, let's do this thing where I just clear off all my writing right here, and then, oh, by the way, I stole this picture. This picture is not mine. I stole this picture from the Museum of Natural History, so thank you so much, Museum of Natural History. I do appreciate you. Okay, moving on. Here you go. Romer's measurements of the periods of the eclipses of Jupiter's moon Io in 1675 led Huygens later to calculate the speed of light to the correct order of magnitude. Again, not the correct number, but he got the times 10 to the 8th part right. But people were not satisfied. They said, you have a number, but it's not the true speed of light. What is the real speed of light? And that's when we had a new friend by the name of Albert Michelson who came on the scene. Albert Michelson designed a great experiment to try to figure out the exact speed of light. And here's what he did, and this is like a rough explanation of what he did. Okay, so this is the Wilson explanation, not like he would give you a different story about how this happened. But here's like the general concept. The general concept is that Mr. Michelson went under the earth and he dug a giant tunnel. Wow, I should try again. He went under the ground and he dug a giant tunnel. This tunnel went from underneath a mountain called Mount San Antonio to underneath Mount Wilson. And then that was a distance of 22 miles. Then he opened up a little slit above the tunnel so that light could filter down into the tunnel. So you had this giant tunnel that's 22 miles all under the ground. You have a mountain over here and a mountain over here. He's sitting underneath the mountain in these tunnels. There's a little bit of light that comes down from the surface, and he says, perfect, I love it, it's brilliant. Then he had this giant, like, octagonal mirror wheel thing. So he had this giant wheel, and on each side, here and 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 also here, he had a mirror on the sides. And here's what he could do is he could give this mirror or this wheel a nice spin, and these mirrors would start all spinning around in circles. So the light would come in for the surface, he'd give this thing a nice crank, and then the mirrors spin, the light bounces off the mirrors, and then it takes a little journey. Here's what would happen. The light would come in, it would hit the top mirror, it would travel the 22 miles to under Mount San Antonio, where there it would hit a mirror. Then it would reflect back, travel back another 22 miles, where it would hit the wheel again. Then that light would bounce off of the wheel, go through a lens, and go into Mr. Michelson's eye, where he was looking to see if he could see the light come, not from the ceiling, but all the way back from San Antonio back to him. Here's the idea. And again, this is the part where this is like Miss Wilson's vague retelling, not like the actual truth. Okay, so his setup was much more elegant than what I'm about to explain to you. Actually, let's just erase everything. Clear all. Okay, here is his setup. What he did is he got rid of all the mirrors except for just one right here. And then here's what he did. Is the light came in, it hit the mirror, and then this thing was spinning. And as the light came in, it hit the top mirror, it bounced back, and then it went all the way over to San Antonio and then bounced back and made it all the way back over here as this thing is spinning. Well, if this thing is spinning too slow, then what would happen was that the light would get all the way back here, and by the time the light got back, the mirror wouldn't have turned far enough. So this mirror, which used to be right here, would now be right here. And what happened was the light would hit this end right here. It would just get absorbed, and then that would be it. And you wouldn't be able to see anything over here. If the mirror was rotating too fast, what would happen would be that this mirror would be spinning. The light would come in, it would hit the top mirror, it would go the 22 miles, it'd get back the 22 miles. By the time it got back, the mirror would be all the way over here because it would have made so much progress in that amount of time. And so the light would hit this little end right here and nothing, it would get absorbed, and then you wouldn't be able to see anything. But if the mirror was going at just the right speed, the mirror would start right here. The light would come in, it would hit the mirror, it'd bounce off, go the 22 miles to Mount San Antonio, go back the 22 miles back to Mount Wilson, and this thing was spinning with such perfect timing that it spun right around until it landed right here, right as the light was getting back. So the light would land here just as the mirror landed here. Well, now Michelson had two things. He had a distance. The light would travel 22 miles this way and 22 miles back. He had a distance of 44 miles. And he had a time. Because he knew how fast this little mirror situation was spinning, he knew how much time it took for the mirror to get from here to here. So he had a distance and he had a time. And with that distance and that time, he was able to calculate a value for the speed of light. And the value for the speed of light that he was able to calculate was equal to the speed of light is 299,792,458 meters per second. Approximately 3.00 times 10 to the 8th meters per second. This now was a real and accurate number for the speed of sound, for the speed of light. And that's the number that we still use, and this is the number that we still rely on today. And actually, we've defined other numbers, like how long a meter is, based on this number, because it turns out that there's nothing more constant than the speed of light. More to come on that later. Well, now, we had a measurement for the speed of light, and there's one other thing that we started to do with it. Okay, and let me see if I can go ahead and just, mouse mode, and shift. You got it, buddy. Go to the next slide. You can do it. I believe in you. It's not that hard. If you think about it, you just change slides. Okay, yes. Oh, yeah, here we go. This was in 1880 when Michelson very accurately calculated the speed of light utilizing a rotating octagonal mirror and light pulses. Yes, that was what we just discussed. Okay, next. Now that we knew the speed of light, we could use the speed of light to actually measure distances, like how far away something is. And this is where the concept of the light year comes from. I kind of want this a little bit bigger. Okay, this is where the concept of the light year comes from. It's this idea that light takes certain amounts of time to get to us. It's not here instantaneously. The light from the sun takes 8 minutes to get to us. And there's light from stars that are very, very far away that takes a lot more time to get to us. So we started to talk about the distance of stars in terms of how long it would take for the light from that star to get to us. And the further away the star is, the more time it takes for the light to get to us. So the light year is a concept that is a measurement. Oh gosh, well, that is not what I wanted. Back. Okay. The light year is a concept for actually, that is totally what I wanted. Wow. Try again. Okay, the light year is a concept that describes the distance that light travels in 1 year. It's a really weird name for something because it sounds like it's a year because it's a light year, which makes it sound like it's an amount of time, but it's really not an amount of time, it's an amount of distance. It's the distance that light travels in 1 year. It's how far light can go in a year. So if I turn on a little flashlight right now, and then that flashlight started to shine out some light, the amount of ground that light could travel in a year, that is 1 light year. And here's a little calculation to show you exactly what that number looks like. Since speed is equal to distance over time, then you can find the distance of a light year by just doing the speed of light times the time of a year. You got to do a little bit of a unit conversion here to go from years to days, and then from days to hours, and then from hours to seconds. But once you type it into your calculator, you should get something like 9.46 times 10 to the 15th meters. That's a crazy distance that light can travel in a year. Students sometimes have a struggling time kind of conceptualizing meters. So we can take a look at this in miles. It's 5.88 times 10 to the 12th miles, which once again is nearly impossible to conceptualize. But that's the distance of a light year. Here's what I like to tell students in classes. I like to tell them, hey, you think that like this number is big, it is crazy, crazy large, but there are stars that are billions of light years away. It's really hard to even begin to grasp the enormous size of our universe. To say that the universe is large is an understatement. You have stars that are billions of light years away from us, and a light year is 5.88 times 10 to the 12th miles. The universe is enormous, is the long story in a very short sentence. The universe is enormous. That means if you're looking at a star that is a billion light years away, you're looking at a star, or I should say you're looking at the light from a star that left the star a billion years ago. When you look at the sun right now, that sun is 8 light minutes away, which means it takes 8 minutes for the light from the sun to get to us. So the sun that you're seeing in the sky right now is not the sun as it actually is, it's the sun as it was 8 minutes ago. If the sun were to suddenly explode in the sky, like suddenly, instantly to vanish, we would not know about it for 8 minutes. We would have 8 minutes on Earth where everything would seem perfectly normal, even though the sun had already exploded. It's the same thing with stars that are very far away. If you have something that's very far away, you would see it as it was a billion years ago, if it's a billion light years away, or 4 billion years ago, if it's 4 billion light years away, or half a century ago, if it's half a century of light years away. So whenever we look at something that's far away, we're not just seeing further in distance, we're also seeing further back in time. Because when we look at stuff that's far away, we're seeing it as it used to be. This is why scientists love using telescopes to try to see a little bit more about what our universe must have been like back in time. Because the further back, the further away we can see, the further back in time we can see. We can see closer and closer and closer to what the beginning of the universe actually looked like. So that's a little bit on the light year. Okay, now I just came to realize that actually I have an issue because I'm recording with Screencastify now, which is great, and this is not an advertisement for Screencastify, but I'm very excited about it because hopefully it'll do better than what I was using before. However, the issue is that I am not yet on a premium subscription plan, and so I can only make videos that are shorter than 30 minutes, and we are quickly approaching that deadline. So I do have a lot to talk to you about when it comes to this next topic, which is what is light, but you can find that information in my next video. So this will be part 1 of a 2-part video series that is a 1-day long lecture on the history of the speed of light and the history of the nature of light. So check out the next video for the rest of the content. Can't wait to see you there, virtually of course. All right, peace out, good people. See you soon.